good? Okay. Yeah. So not my student, not my postdoc, senior faculty, and he was asked in a bunch of places that, are you a student of Ankush? And he was not happy about that. All right. So yeah, today I will be talking about parametric choreographies, specifically describing this language paracore. And these are basically choreographies over party sets. And I will explain what that means. Okay, so just a little bit of motivation. As we know, many protocols out there, specifically distributed protocols, have parametric number of parties. And when I say parametric, I don't mean dynamic. I mean something like two-phase commit or MapReduce, any of these protocols where the number of parties don't evolve during the protocol execution, but they may be deployed with different number of parties at the start. So you may want to deploy a protocol with n participants, like 5 participants, and then with 10 participants, and so on and so forth. But during the protocol execution, they don't evolve. And so there are many examples of this, like two-phase commit, which has 1 coordinator, P participants, MapReduce, which has 1 coordinator, and mappers are reducers, and so on and so forth. Okay, and so many traditional choreographic languages generally support a constant number of parties, although there has been a lot of recent work on supporting more than that. So our effort is in that way of supporting more than just a constant number of parties. And the goal of the language is that to deploy the protocol on different number of parties, I should not have to re-implement the program. I should write the choreography once and then deploy it on different parties without rewriting anything. Okay, and so I will first give you a very, very high level description of what are the main features of the language, and then I will show you some examples and then some theory. Okay, so we have the standard expressions like P.E, which is a local expression at a party, P.E communicated with Q.X, meaning the party P communicates the value of expression E to a party Q, which binds it to a variable X. We have conditional branching, and we have synchronization labels like L and R to communicate whoever did the branch to other parties which branch it took. And we have only 2 new constructs into the language, which is one is a for loop over party sets. So here I have a for P in capital P, which here capital P is a set of parties, and P is a party variable that iterates over that set of parties. And then C1 is the body of the loop. And so you're basically executing choreography C1 for all the parties in capital P. And then C2 is the loop continuation, so the choreography that executes after the loop is finished. And then we have an associative array communication. I'll explain what this means a little bit later, but the high-level idea is that when you're collecting values from a parametric number of parties, you generally want to store that in an array, which is indexed with the same parties that you're collecting the values from. Okay, and so before I go to an example, I wanted to just highlight a little bit more about the language. As I showed you already, we have party variables like P. These party sets, capital P, they are pairwise disjoint. So you can have many party sets in the program, but they are all pairwise disjoint. And this gives us this property of no self-communication, and which also gives us deadlock freedom. I already talked a little bit about associative arrays. And then one point that I will come back to later, but we have a projection algorithm that's linear time, and there are no runtime checks in the projected program. Okay, so this is an example of the two-phase commit protocol in our language. But before I go through the choreography itself, I just want to give a high-level description of the protocol. So in this protocol, there is 1 coordinator, n participants, and collectively they want to decide to either commit a transaction or abort a transaction. And so this happens in 2 phases, hence the name two-phase commit. In the first phase, the coordinator sends a prepare message to all the participants, and the participants individually decide whether they want to commit or abort. And then based on that, they compute a vote, and they send it back to the coordinator. So the vote will be either yes or no, depending on whether the participant wants to commit or abort. Then the coordinator collects all these votes, and then it counts the votes. And if every participant votes yes, then the coordinator decides to commit. Otherwise, it decides to abort. If the coordinator decides to commit, then it sends this L message to all the participants. And if it decides to abort, then it sends the R message. And then after receiving this L or R message, the participants will either commit or abort. OK, so now I will go through this step by step for this program. So starting with a for loop over all participants. So participants here is a party set. And this P represents for one abstract party in that set. And so you are sending this prepare message to each participant. And because you don't really, in this example, I don't care about the data. Usually there is some transaction data associated with the prepare message. But because I don't care about it, I just used an underscore that it just receives a message and just ignores it. OK. So that's the first loop. One interesting aspect that I want to highlight is that the semantics of our language are designed in a way that this for loop treats this participant set basically as an unordered set. So the semantics is non-deterministic in choosing the order in which you iterate over these participants. So we don't have to fix an order. And the language is designed that way. The projection, all of that handles for this kind of non-determinism. OK, so that's the first loop. This is where the prepare message is sent to all the participants. Then you want to collect the votes from the participants. So internally, what each participant would do is call the prepare function. And usually, this is the transaction information that it gets from the prepare message. But again, I ignored that. And so it calls this prepare function locally. Each participant does that, computes the vote. And then the vote is sent back to the coordinator. And the coordinator is storing that in this associative array called votes, which is indexed by the same party P, that is the sender of the vote. And again, the reason we need an array is because if I just used a regular variable here, then it would repeatedly get overwritten as you're executing different iterations of the loop. And we don't want to do that. We want to actually collect all these values. And so we use an array for that. And this is actually enforced by our type system that whenever you have a parametric party, like P, sending to a different party, it must always send to an associative array, which is indexed by the same party P, which is the sender. So that's enforced by our type system. OK, so that ends the first phase. Now the coordinator has to make a decision. So it will take this votes array, call this count votes function, which will just count the number of yes and no votes. And based on that, the coordinator makes a decision whether it wants to commit or not. And this naturally acts as a barrier between the first and the second phase. As you can see, that the first phase has to fully finish before the second phase starts, because the coordinator has like a data dependency here. It has to complete this decision, for which it has to wait for all the votes to come in. And therefore, our semantics ensures, even though it can do out of order execution, that the first phase must fully finish before the second phase starts. OK. Say that again? No, we don't need a construct to specify a barrier. Maybe in some situations you may need to, but here it is tracked directly by the semantics. Because this line depends on votes being calculated, and votes is being received here. And the coordinator is involved in the communication that comes later. So the coordinator cannot do this, or any of the participants cannot do this until this decision is computed. It's an aggregation operation, yeah. OK. So that's the first phase. In the second phase, now you again iterate over all the participants. And based on the decision of the coordinator, you either send the L message if the coordinator decides to commit. and you send the R message if the coordinator decides to abort. And accordingly, in the then branch P, every participant P commits, and in the else branch, every participant aborts. And again, why do we need these synchronization labels? Because the behavior of the participant depends on whether it receives or whether what decision the coordinator makes, and therefore the coordinator needs to send its decision to all the participants. Okay. And so before I talk more about the theory of our language, I wanted to quickly come back to this point that you want to implement the program once, but you want to deploy it with different number of participants. And to show that, I wanted to show how the pipeline of our language works. So there are 3 phases. One is where the programmer writes the choreography. This is where type checking also happens. And at this stage, you assume that party sets are fully abstract. You have no idea what parties belong in each set. The only thing you know is that party sets are mutually disjoint from each other. Beyond that, you have no other information. Yeah. They can be empty, yes. I don't think in any of our examples we used empty sets, but they can be empty. There is nothing preventing that. Yeah. Actually, that's a good point. I will come to a semantic rule in 5 slides that will answer that question, which I just realized. Okay, so yeah, in the first phase, you are writing and type checking the choreography. And then in the second phase, this is where you are instantiating the party sets. So this is basically like saying that, okay, this participant set contains these specific parties. This is given as an input to the endpoint projection algorithm. So the endpoint projection algorithm takes the choreography, takes this instantiation, and then generates the control programs. Yeah. What do you mean I treat everything uniformly? No, the coordinator gets a different, like every party in a party set gets the same code, but there can be many different sets, and a party in a set, like in different sets, can get different code. You can even think of the coordinator as a singleton set. Yeah. Okay. So then you are instantiating, and the reason we are instantiating the party sets here, we can even show that we maybe don't even need to do it here, is that the control programs that are now generated, they're fully executable, because everything that was abstract, namely the party sets, have been fully concretized. So at this point, there is no non-determinism, no unknowns. Everything is fully determined. And so these are executable, and then we deploy these programs, and then you can execute them. And this is another point to see here, is that if you want to deploy the same choreography with different party sets, then you just have to change phase 2. You don't have to rewrite the choreography. Okay. So now coming to the endpoint projection. So here I will talk about the choreography's first projection on the coordinator, and then I will show the projection on the participants. And the main thing to note here is that a for loop generally would project to a for loop for any parties that are outside the set that it is being iterated on, but will translate to or project to one iteration for any parties that are inside the set. And so because the coordinator is not in this participant set, this for loop will translate into a for loop for the coordinator. So it will just say send prepare to all the participants. Then in the next for loop, here this is local computation at the participant, so the coordinator doesn't care about that. The only thing it does is that it receives votes indexed by P from the party P. Then you compute the decision based on calling the count votes function on the votes associative array. And then again, you have another for loop where based on the decision, you either send the L message to P or the R message to P. And then there is some return, which you can ignore the return. Choreographies don't need to return, but here we are requiring them to. So that's the projection on a coordinator. And then comes the projection on a participant, which as you can see is much smaller. And that is because it doesn't have any loops. All the loops go away because each participant is essentially executing just one iteration of the loop. And so this for loop just translates to receive a single message from the coordinator. This for loop translates to two instructions. First, compute the vote, and then send the vote to the coordinator. And there's no actions here for the participant. And again, this translates to another a single action, which is you receive either the L message or the R message. If you receive the L message, then you call commit. Otherwise, you call abort. OK. So that's the example. And yeah, I have time. OK. So in the last 5 minutes, I will talk a little bit about the meta theory of the language, starting with the semantics. So traditionally, maybe not traditionally because there are both kinds, but our language is functional, and but we use this environment-based semantics. So instead of just saying C1 steps to C2, I have this environment which stores mappings of this form, p.x maps to v, saying that at party p, variable x has value v. And this is a bit technical, why we need that. So I will ignore it, but if you have questions, I'm happy to answer. So it contains mappings of this form. And this judgment is stating that choreography C1 with environment sigma 1 steps to choreography C2 with environment sigma 2. And R and B are, R is the readx label. And this is something we use when we are proving operational correspondence. And B is a blocked set which tracks which parties can take a step, which parties are blocked. This is like both of these are standard for choreographic languages. OK, so there are lots and lots of rules. I think there's at least 5 or 6 pages of rules in the language, and I will not explain all of those. I will just focus on some of the rules that relate to the for loop. The rest of the rules are pretty standard. And so the first rule is what to do when you have a for loop like this. For some xp in this set p, you execute C1 followed by C2. So here is where the non-determinism comes in, where I was saying that you choose any arbitrary order of loops, of a for loop. So here I pick non-deterministically a concrete party C belonging to that set. And then I pull out one iteration of the for loop. And I'm saying this choreography C1 executes under this environment sigma 1. And all that sigma 1 is basically what sigma is, except this variable xp is now mapped to C, because I'm iterating on that particular iteration where xp is C. And then I compose this iteration with the remaining iterations. So p prime here is basically the original set p minus the party C. So it's like not very different from a traditional for loop where you take one iteration out and you compose it with the rest of the iterations. And then you have the base case of this where you will keep doing this. Eventually, this party set P will become empty because you finished all the iterations. And that's covered by this rule where this party set is empty. So this answers your question. What if the party set is empty? We have a rule for that. Thank God. And so if the party set is empty, then you just transition to C2 because you've exhausted all the iterations. This rule may look a little bit complicated, but it's not really. This is stepping one iteration of the for loop. So I'm saying if sigma 1 C1 steps to sigma 1 prime C1 prime, then this whole choreography steps to, instead of having sigma 1 C1, now I have sigma 1 prime C1 prime. And I also update this global store sigma prime. I'm not going to go into details on why we need to do that, but it is to prove soundness. And so you keep stepping this internal iteration. Eventually, it steps to end, meaning that the iteration is over. And at that point, you get rid of this iteration, and you go back to executing the remaining iterations of the for loop. OK. So A couple of theorems about the language. We have the standard theorems of progress and preservation. I didn't talk at all about the type system because there isn't anything very interesting happening at the type system level. The only interesting thing is that the type system is enforcing that there is no self-communication, and it's using the fact that party sets are disjoint. But this progress theorem is basically saying that if you have a well-typed choreography, then either it's already a value, or there exists a new choreography and a new environment, sigma prime C prime, such that sigma C steps to sigma prime C prime. And then you have a preservation theorem, which is also very standard, saying that if you have a well-typed choreography and it takes a step, then you can ignore all that. But the new choreography that you will get will also be well-typed. And then we have the standard operational correspondence theorems in both directions. Again, this may look complicated, but it's not really. This is basically saying that if the choreography takes a step, a single step, then you project this choreography down to a system, pi. And basically, this theorem is saying that if the choreography can take a step, then the corresponding system can also take a step. And this is where the readx label R comes into play, because the step that the system takes is somehow related to the step that the choreography takes. And this is this relation. So this is the forward direction. Then there's the backward direction, where if the system is taking a step, then and the system is basically a projection of a well-typed choreography, then you can also show that the choreography will take a corresponding step. And with the same things that the step will be related, and the new choreography will be a projection of, the new system pi prime will be a projection of C prime. Okay, and so we also have implemented this language, or like basically an interpreter for this language. And we tested it on a few different protocols. And here I'm basically showing the number of lines of code of the choreography versus the endpoint projection. And in general, we found that choreographies lead to something between 15 to 60% reduction in the lines of code that you have to write if you were writing a choreography versus writing the endpoint projections directly. And our endpoint projection algorithm is quite fast. Even with 15 parties, the code that is generated in less than 2 milliseconds. And I'm not going to go into other results, but we can show that the generated control programs are also efficient. They scale linearly as you increase the number of participants. Okay, so just to summarize, so what was new? The only thing really that was new was we introduced this for loop with abstract party sets that were unknown during type checking, but were later concretized. And we support out-of-order execution. We have linear time endpoint projection. The theorems, we have deadlock freedom because we have progress and we have operational correspondence. And so, yeah, I already talked about that. And we have an implementation that we tested on a few different protocols. And I had showed you the results. So this is it. Thank you.
We have time for one quick question.
Yeah.
Your meta-theoretic results, they are proven regardless of instantiation of party sets, or they hold for a particular instantiation of a party set?
No, they hold for a, because when you are doing the semantic step, the semantic step only applies to an instantiation. So when you are really showing progress in preservation, you are doing one instantiation, and you're saying that this is like a runtime choreography. It takes a step, so it's a concrete one. It's an instantiated one.
All right, I'm afraid we are out of time, but let's thank Ankush again.